And we're going to revisit the MNIST handwriting recognition problem where we try to classify a bunch of images of people drawing the numbers 0 through 9 and see if we can do a better job of it using CNNs. Again, CNNs are better suited to image data in general, especially if you don't know exactly where the feature you're looking for is within your image. So we should expect to get better results here. All right, so we're going to start by importing all the stuff we need from Keras. We're going to import the MNIST dataset that we're playing with, the sequential model so we can assemble our neural network, and then we're going to import all these different layer types that we talked about in the slides, the dense, dropout, conv 2D, max pooling 2D, and flatten layer types. And in this example, we'll use the rmsprop optimizer. Go ahead and kick that off. And the rest here for loading up the training and test data is going to look just like it did before. Still waiting for that Keras to initialize itself there. All right, so that should load up the MNIST data set. We're going to shape this data a little bit differently. So since convolutional neural networks can process 2D data in all their 2D glory, we're not going to reshape that data into flat 1D arrays of 768 pixels. Instead, we're going to shape it into the width times the length times the number of color channels. So in this case, our data is grayscale in nature, so there's only a single color channel that just defines how wide or dark the image is, the specific pixel is. And there's a couple of different ways that data can be stored. So we need to handle a couple of different cases here. It might be organized as color channels by width times length, or it might be width times length times color channels. So this is what this little bit of code here is dealing with. But either way, we will see if it's a channels first format or not and reshape the data accordingly. And we're going to store that shape in this thing called input shape. So that's the shape of our input test data and train data for that matter. As before, we're going to scale this data down so it comes in as 8-bit byte data, and we need to convert that into normalized floating point data instead. So we'll convert that data to floating point 32-bit values and then divide each pixel by 255 to transform that into some number between 0 and 1. Go ahead and hit Shift Enter in there to kick that off. All right, and as before, we will convert the label data into one-hot categorical format because that will match up nicely with the output of our neural network. And nothing different here. We're just going to, again, do a sanity check to make sure that we successfully imported our data. So we'll pick a random training set sample to print out here and display. And there's the one-hot format of the 3 label, 0, 1, 2, 3. That's correct. Human readable format 3, and it looks like that. Sure enough, that looks like the number 3. So it looks like our data is in good shape for processing. So now let's actually set up a CNN and see how that works. So let's walk through what's going on in this next code block here. As before, we start off by setting up a sequential model that just allows us to very easily build up layers to build up our neural network here. And we will start with a conv 2D layer. So what this syntax here means is that our convolutional 2D layer is going to have 32 windows, or 32 regional fields, if you will, that it will use to sample that image with. And each one of those samples will be of a 3x3 kernel size. It also needs to know the shape of your input data, which we stored previously. That's the 1 by 28 by 28 or 28 by 28 by 1, depending on the input format there. We will then add a second convolutional filter on top of that to hopefully identify higher level features. This one will have 64 kernels, also of 3 by 3 size, and we are going to use a ReLU activation function on that as well. So we've built up 2 convolution layers here. And again, you want to just reuse any previous research you can do for a given problem. There are so many ways to configure CNNs that if you start from scratch, you're going to have a very hard time to tune it, especially when you consider how long it takes to iterate between each run. These are very resource intensive. So I've just taken this from the CNN example that comes with the Keras library and drawn my initial topology from it. So now that we've done our convolution layers, we're going to do a max pooling 2D step to actually reduce that down a little bit. So we're going to take a 2x2 pool size, and for each 2x2 pixel block at this stage, we're going to reduce that down to a single pixel that represents the maximum pixel found within that pool. So note that the pool size can be different from the underlying kernel size from the convolution you did. So really this is just a technique for shrinking your data down to something that's more manageable. At this point, we'll do a dropout pass to prevent overfitting. We will then flatten what we have so far. So that will take our 2D data and flatten it to a 1D layer. And from this point, it's just going to look like any other multi-layer perceptron, just like we used before. So all the magic of CNNs has happened at this point, and now we're just going to convert it down to a flat layer that we input into a hidden layer of neurons. In this case, we're going to have 128 in that layer. Again, with a ReLU activation function, we'll do one more dropout pass to prevent overfitting, and finally choose our final categorization of the numbers 0 through 9 by building one final output layer of 10 neurons with the softmax activation function on it. All right, so let's go ahead and let that run. Again, nothing's really happening until we actually kick off the model, so that doesn't take any time at all. We can do a model.summary just to double check that everything is the way that we intended it to be. And you can see that we have our two convolution layers here, followed by a pooling layer, followed by a dropout, a flatten, and from there we have a dense dropout and dense multi-layer perceptron to actually do our final classification. All right, finally we need to compile that model with a specific optimizer and loss function. In this case, we're going to use the atom optimizer and categorical cross entropy because that's the appropriate loss function for a multiple category classification problem. And finally, we will actually run it. Now, like I said, CNNs are very expensive to run. So let me talk about what this command does first of all. Nothing unusual here. It just says that we're going to run batches of 32, which is smaller than before because there is a much higher computational cost to this. We're only going to run 10 epochs this time because, again, it takes a long time. More would be better, but there's only so much we have time to do. Verbosity level 2 because that's what you want to choose for running within an IPython notebook, and we will pass in our validation test data for it to work with as well. Now, I am not going to actually run this because this could actually take about an hour to run. And if you don't have a beefy machine, it might not finish at all. You know, if you don't have enough RAM or enough CPU power, this might even be too much for one system. So I'm going to skip ahead here. I actually ran this earlier, and it did take about 45 minutes. But you can see that it very quickly converged to a very good accuracy value here, and it was still increasing. So there probably would have been value to going even beyond 10 iterations of the training here. But even after just 10 epochs or 10 iterations, we ended up with an accuracy of over 99%. And we can actually evaluate that based on our test data and recreate that 99% accuracy. So that's kind of awesome. So CNNs definitely worth doing if accuracy is key. And for applications where lives are at stake, such as a self-driving car, obviously that's worth the effort, right? You want complete accuracy of detecting if there's a stop sign in front of you, ideally, right? Even 0.1% error is going to be unacceptable in a situation like that. So that's the power of CNNs. They are more complicated. They take a lot more time to run. But as we said, the power of Tensorflow, which Keras is running on top of, means that you can distribute this work across an entire cloud of computers and an entire array of GPUs that are on each computer. So there are ways of accelerating this. We're just not taking advantage of that in this little example here. It's just illustrative. So there you have it, your first convolutional neural network, and you can see how powerful it is in successfully doing image classification, among other things. So cool, let's move on to another type of neural network next.